In this video here, we're going to take a look at hyperbolas. So as we worked through the previous chapter on conic sections 1, we introduced rectangular hyperbola with the following equations here. So x equals ct and y is equal to c over t, where t belongs to the set of real numbers and t cannot be equal to 0. So c here is just a positive constant. So just recalling that the Cartesian equation of this rectangular hyperbola is xy is equal to c squared. And this family of curves have perpendicular asymptotes at x equals 0 and y equals 0. So in other words, the x-axis and the y-axis. And a general point on the curve P here has the following coordinates. So P has coordinates of ct and c over t. So moving on then to hyperbolas now. In this case here, hyperbolas do not need to have perpendicular asymptotes. So moving on then, the Cartesian equation of the standard hyperbola is defined as follows here. So we get x squared over a squared minus y squared over b squared is equal to 1 here. So just notice then this is very similar to the Cartesian equation of the standard ellipse, right? The only difference here is rather than a plus, we now have a minus. And if we also quickly draw a sketch here then of the standard hyperbola, as we can see here, we get x squared over a squared minus y squared over b squared equals 1. So it's just the standard hyperbola here. And as you can see then, we kind of get this arc shape here, right? It cuts through at a, and same again here. This cuts through at minus a. And we also have the equations here of the asymptotes. So we get y equals b over ax. And we also have y equals minus b over ax here. So as we can see then, when y equals 0, x squared is equal to a squared. And in that case, then x is equal to plus or minus a, right? So that just corresponds to these 2 points here. So just quickly mark that on the diagram. So minus a here and positive a here. And as x and y tend to infinity, we can also see that x squared over a squared is approximately y squared over b squared. And in that case then, the equations of the asymptotes are given as y equals plus or minus b over ax here, which we've already discussed, right? We've already mentioned that here. We get y equals b over ax and y equals minus b over ax here, okay? And then finally, just note here that the equations of the asymptotes are given in the formula booklet, so it's not something that you do need to worry about memorizing, which is always a good thing, right? So to conclude our introduction here to hyperbolas, let's just have a look then at defining the standard hyperbola in terms of parametric equations. So just as we saw for ellipses, we can define the standard hyperbola in terms of parametric equations. So the standard hyperbola has the following parametric equations here. So x is equal to plus or minus a cos t and y is equal to b sin t, for t belonging to the set of real numbers. Now the standard hyperbola also has alternative parametric equations. So x is equal to a sec theta, y is equal to b tan theta for theta between minus pi, and theta cannot equal plus or minus pi over 2. And then finally here, a general point P on a hyperbola has the following coordinates. So we have plus or minus a cos t, b sin t, or a sec theta, b tan theta, right? And they just come from these 2 definitions here then of the standard hyperbola in terms of parametric equations. Okay, so that gives us everything that we need here then for hyperbolas. Let's just have a look now at 2 practice questions. So let's get started here then with question 1. So for question 1 here, as we can see, right, the hyperbola h has the following equation. So we have 4x squared minus y squared equals 16. So for the first part of this question here, part A, all we want to do is sketch the hyperbola h. So the first thing that we should do here is get this equation here for the hyperbola h into its standard form. And to do that here, all we need to do, right, is divide through by 16. So this needs to be equal to 1. So to do that here, just divide through by 16. So in that case, then what I get here is x squared over 4. So x squared over 4. We then get minus y squared over 16. So minus y squared over 16. And this here then is equal to 1. Okay. So from here then, we can now identify the values of a and the value of b. So a here, Well, this value here then is a squared, so a is the square root of that. So a is 2. And this value here is b squared. So in that case, then b is equal to 4. Okay. So this value of a here, that shows us where the hyperbola h will cut through the x-axis. So we know it cuts through at 2, and it also cuts through at -2. Okay. So altogether then, we'll get something that looks like this here. Okay. And same again here for -2. Let's hope I can sketch this neatly. There we go. That's not too bad. So this here then is my sketch of h here, but we're not quite done because what I also need is the asymptotes of h, right? So we know then that the asymptotes here go through 0. Okay. If I draw these on here, we'll get something like that. Okay, clearly it shouldn't touch the curves. It's asymptotes, so they don't touch. And then I've also got one here going across this way. So again, starts at the origin, like so. And same again here. Okay, there we have it. That's not too bad of a sketch there. So that gives us the solution there to part A. Now for part B then, it says state the equations of the asymptotes of h. So just a quick follow on then from part A. So don't forget then, the equations of the asymptotes are given as follows. So the equation of the asymptotes here, equation of asymptote here, equation of asymptotes here is given as follows. So it's y is equal to plus or minus b over a x here. Okay, or b over a times x, whichever way you want to say that. So b here is 4, a is 2. So as we can see then, the equation here of our asymptotes is given as y equals plus or minus 4 over 2x here. We simply get 2x there. Okay. And there we have it. So that gives us the solution to part B and the solution to question 1. So moving on to the very last question here, question 2, where as we can see then, the hyperbola h has the following parametric equations here. Now for the first part of this question, then part A, all we want to do is find a Cartesian equation for the hyperbola h. So to get us started here then, for part A, what we need to do here is use one of our trigonometric identities from A-Level Maths. So we're going to use here sec squared theta minus tan squared theta is identical to 1. Okay, so sec squared theta minus tan squared theta is identical to 1. So what I'm going to do here then is rearrange my parametric equations in terms of sec theta and tan theta, and then we can use our trig identity here. So in that case then, let's do that up here. As we can see then, sec theta is equal to x over 4. And then for this one here, tan theta is equal to y over 2. So hopefully nice and straightforward there, like so. So now we can use our trig identity here. So in that case then, sec squared theta, that's sec theta all squared. So I get x over 4 squared. So that gives us x squared over 16. Okay. Doing the same here then with tan theta, we get minus y over 2 all squared. So that gives us minus y squared over 4. Okay. And this here then is equal to 1. So that gives us the solution to part A, hopefully nice and straightforward there. So moving on now, let's have a go then at part B here. So for part B then we need two things here. I need the value of A and the value of B. So this value here, this is A squared. So in that case then A is 4. And this value here is B squared. So B in that case is 2. Okay. So to sketch the hyperbola h here, well, A tells us where it cuts through the x-axis. So we know then it's going to cut through at 4. And it's also going to cut through at -4. Okay. So if I attempt to sketch this here, let's see how this goes. Like so. It's not brilliant, but you get the idea. We've got that kind of arc shape here. I'm doing the same then at -4. It's not too bad. So we're not done quite here though, because what I also need is my asymptotes here. So my asymptotes cut through the origin, 0, 0. And this should clearly be a straight line here. I'm doing it freehand, so it's not perfect, but this here then is a straight line. I'll also go down as follows. It's an asymptote, so it shouldn't touch the curve here. And same again then, going up this way. As I'm doing this freehand, so it's not perfect, but you get the idea. I'm going down as well. Okay, like so. So they are my asymptotes here. What we have then is a sketch of H here. Okay, so there we have it. That gives us the solution to part B. And then finally here for part C, let's do that underneath here. It says state the equations of the asymptotes of H here. So for the equations of the asymptotes then, don't forget here that they're given as y equals plus or minus b over a x. So b over a x here, like so. We've got the value of b, we've got the value of a. So in that case then, nice and straightforward here for part C. As we can see then, y is equal to plus or minus, so it's b over a, so it's 2 over 4, which is just the same as a half, right? 1 over 2. We get 1 over 2 x there. Okay, so we get y equals a half x and y equals minus a half x there. That gives us the equations of the asymptotes of H. So that gives us the solution there to part C. And that actually gives us the solution then to the very last question here, question 2. And that brings the end then of this video here on hyperbolas.